I'll be talking about memory allocator security. So my name is Yves Yunan, and I'm a researcher at the DistriNet research group at the Catholic University of Leuven. I'm also a member of the No Login Security Research Group. So I'll start off by giving an introduction, then I'll talk about which attacks I will be describing. I'll describe these attacks in general terms, then I'll apply them to different memory allocators. I'll describe our own version of a more safer allocator, other safer allocators, and I'll also tell you why ours is better than theirs. And finally, I'll present our conclusion. So many allocators ignore security because they were designed to be fast and limit waste. So while these are noble goals, today security has become so important that we should also implement security in the memory allocator. Because they ignore security, they can often be be abused to perform code injection attacks. And we want to show that more security is possible at a relatively low cost. I'll be describing 3 attacks on memory allocators. Well, actually 2 attacks, and one is a specialized version of the first attack. So first, heap-based buffer overflows. So the heap is memory that is dynamically allocated at runtime, and overflows can also occur in this memory, of course. But since no return address is available, attackers must overwrite something else to be able to exploit it. An attacker could overwrite a data pointer or a function pointer which is stored in the heap, but these are not always available. So a more reliable technique is to overwrite the memory management information which is stored together with a chunk which is allocated on the heap. An off by 1 and off by a few bytes is a special case of buffer overflow. For these overflows, limited space is needed. Usually these are only exploitable on little endian machines, at least off by 1s are, because the least significant bit is stored before the most significant bit on those architectures. And off by a few bytes don't occur that often, but they demonstrate low space attacks. Dangling pointer references are pointers to memory that is no longer allocated. Dereferencing such memory is not checked in C, so generally this would lead to a crash, but when used together with the memory allocator, they could turn into a code injection attack when memory is deallocated twice, for example, because you could overwrite the memory management information. Okay, let's apply these attacks to several memory allocators. So I'll start by describing Doug Liez's memory allocator. On this, Linux uses a memory allocator which is based on this allocator. So they've improved it slightly for better performance for threading, but the main information is about the same. So in this allocator, every allocation is represented by a chunk, and the memory management information for a particular chunk is stored together with a chunk. When a chunk is freed, it's stored in a doubly linked list of free chunks. And an invariant of this allocator is that 2 bordering free chunks are always coalesced into a larger chunk. We'll base our description here on dlmalloc 2.7.2. And attacks on Doug Liez's memory allocator were first described by a Solar Designer in an exploit. So this is what a chunk looks like in this allocator, an allocated chunk. So chunk 1 contains the size of the physically previous chunk, the size of its followed by the size of its own chunk, and then it has space for the user data. So the user can write into this space. A free chunk looks like this. So again, the size of the physically previous followed by the size of its own chunk. However, the user data has been overwritten with a forward pointer, which points to next free chunk, and a backward pointer, which points to a previous free chunk. So in this case, chunk 4 is the first free chunk 2 is the second free chunk, and chunk 3 is the last free chunk. When such a chunk is removed from the doubly linked list of free chunks, the following code is executed. So first we get the forward of the current chunk, which we are unlinking, the back of the current chunk, and then we use the forwards backward. We set the forwards backward pointers to the back pointer and the backwards forward pointer to the forward pointer. This results in the chunk being removed from the list. However, if an overflow occurs in this memory, the attacker will be able to overwrite everything in chunk 2 if the overflow is in chunk 1. So in this case, the attacker has injected his code into chunk 1, and he modifies the forward pointer and makes it point to the return address. This can be used to overwrite arbitrary memory locations, as all the examples I will give, but we'll always use the return address as a location to overwrite. And then he makes the backward pointer point to his injected code. So now when the chunk is unlinked, the return address will be dereferenced, and the value of the backward pointer will be placed in over the return address. As a result, when the function returns, the attacker's code will be executed. I've left out some specific details, which I've described in a paper which is linked to this talk. So this is just a general idea, but I've simplified it a bit, so that you can follow the talk. So an off by one in the malloc is also possible. So chunks are always multiple of 8 bytes. So and as a result, the last 3 bits of the size field of the chunk are unused, and those are then used for information about the specific chunk. So in the malloc, it's used for 2 specific flags to mark if the chunk is mapped or not, and if the previous chunk is in use or not. To be able to do an off by one on the malloc, the 2 chunks must be right next to each other. So they must not be padded up to a multiple of 8 bytes. When this occurs, the previous size field of the next chunk will be used for data as well. This is to save some bytes by using it for data. So when an off by one occurs, as a result, we can overflow the size of chunk 2. We can overflow the least significant byte of the size of chunk 2, and we can set the prev in use bit to 0. Since the previous size field is used for data, we can just put in a smaller size for the previous size field, and when chunk 1 is later unlinked via chunk 2, because for coalescing, for example, it'll use this, it'll point into the smaller chunk, so the smaller size. So if we store a fake chunk in this space, which has a forward pointer, which again points to the return address, and a backward pointer, which points to the injected code, the unlink again will overwrite the return address with a pointer to the injected code. And the code will be executed when the function returns. Double free can occur in DL malloc and is exploitable. So in this case, chunk 1 is a free chunk of a larger size, and chunk 2 and 3 are the same size, and they're stored in a doubly linked list. When a chunk is freed, it's placed in the beginning of the list of free chunks of the same size. So if chunk 2 would be freed twice, it would be placed in the list again, and because due to the way it's placed into the list, it'll actually point to itself. However, when the chunk is reused, so for example, if we request a chunk of the same size, we'll get the first chunk in the list of free chunks. Chunk 2 will be returned, but it won't be unlinked because the forward pointer's backward pointer points to the chunk itself, and so on. So chunk 2 will still be in the list, but the attacker will now be able to write in this area. So since the attacker can now modify the forward and backward pointer, he can again make it point to the return address and his injected code. And when chunk 2 is now unlinked again, since it's still in the list, it can get unlinked again, the return address will be overwritten again. So our conclusion for this allocator is that it's vulnerable to heap overflows, off-by-ones, and double freeze. Version 2.8 contains some mitigation techniques for these attacks, but we'll describe those in our related work section. CSRI and QuickFit are allocators which are very closely related to the malloc. So I won't go into too much detail, but I'll just give a quick overview of these allocators. So they both have the same representation when a chunk is in use. So at the top of the chunk is the size is stored, and at the bottom of a chunk, we also have the size of the chunk. The least significant bit of the size is used to denote if the current chunk is in use or not. In CSRI, when a chunk is freed, it looks like this. So it still contains the size of its chunks in the same positions. The use bit is set to 0, of course. And the previous and next pointers are stored at the end of the chunk. The old user data is overwritten with the hex value 125, so that the program would more likely crash if data is read from this location. QuickFit looks very much like dlmalloc, so we won't talk about exploiting QuickFit. So it uses the same forward and previous pointer stored right after the chunk size. An overflow in CSRI looks like this. So chunk 1 is again a chunk which is allocated and which will be overflowed, and chunk 2 is a free chunk which is stored in a list of free chunks. So when we overflow chunk 2, we can again make the previous pointer, in this case then, point to the return address, and the next pointer point to the injected code, and again when unlinking occurs, the code will be executed. So this is pretty similar to dlmalloc. A double free is not possible in this case because the in-use bit is checked before a freeing operation occurs. And off by 1 and off by 5 is not possible because the size of the chunk at the beginning is compared to the size of the chunk at the end. So if we'd modify this, it would result in an error, and the code would not be executed. PHK-malloc is the allocator used in FreeBSD. However, it's used in other BSDs as well by now. And it's the only allocator that we've looked at that takes advantage of the virtual memory system. It tries to minimize the pages that are used by the allocator. So it makes sure that objects that are smaller or equal to page size do not span multiple pages. To do all this, it has two layers on which it operates, the page layer and the chunk layer. Attacks for this allocator were first described by BBP. So the page layer manages allocation and freeing of pages. Information about the page, which is allocated to the heap, is stored in a page directory. This page directory contains, and the first elements in the page directory contain pointers to linked list of page information, which is for each possible size of chunks. So the size of chunks is pretty limited in this allocator, as I'll describe later. And for a particular size, there's a list of the chunk information. There's a list of the pages which contain chunks of that size. And other elements in the page directory contain information about a particular page. So malloc not mine is a page which is not allocated by PHK. Malloc free is a page that's free. And malloc first and follow are used for multi-page objects. So the first page for the multi-page object will be first, and the following pages will be marked as malloc follow. So this is an example of what it could look like. So the heap in this case contains two free pages, a large multi-page chunk, a free page, and a page with small chunks. So we have the first element contains pointers to a PG info list, followed by information about particular pages. So malloc free for the free pages, and first for the first page of the multi-page chunk, and follow for the next page of the multi-page chunk. And again, for a page which is in use, it will have a pointer to its page information. More on this later. So free pages are stored in a sorted doubly linked list based on address, and adjacent free pages are coalesced, and only a pointer to the first page is kept. So this is stored in the page free information. This page free information block is stored using malloc itself, so it mallocs a chunk of memory to store the page free information. This allows the page to be swapped out when it's not in use for a long time, because the allocator just checks the page free information if it should use a chunk or not. So this is an example of the page free information block. So for a page free, we have the next and previous, which store the doubly linked list of free pages, a pointer to the free page itself, and to the last free page. So the first two free pages have been coalesced, so there's only one page free for that area of free pages. And it also contains the size. So the second free page just has page free information, which has and the beginning of the page and the end of the page point to the same page, because there's only one in this area. So as you can see here, the page free information is stored in a area which stores chunk of that size. The chunk layer is the other layer of the PHK malloc. So it has three different types of chunks: small, medium, or large. Large chunks are chunks which are larger than half a page. These are allocated on a single page. And so it will search for a page on which the object will fit, and then set malloc first and follow in the page directory. And that's all the information it keeps for a large page. For small or medium chunks, these chunks are rounded up to the next power of 2, and on a page which contains a particular size of chunks, it will only store chunks of the same size. So for every small or medium page, it stores a page information chunk, and for small pages, these are stored at the beginning of the small chunks. However, for large pages, they're stored again using malloc. And the entry in the page directory points to this page information. So another example. So we've got 3 pages here. Page 1 and page 2 are medium-sized, and page 3 contains small chunks. So the page directory for that, well, page 1 and page 2 contain chunks of the same size. So the page directory for chunks of that size points to the linked list of page informations for that chunk, for that page. And the directory entry for example, for the page with small chunks is stored in that particular page in the page directory. Page information contains the following fields. So the next pointer points to the next page information for the linked list for pages of that size. It contains a pointer to the page itself. And it contains the size and some other information, which I'll not describe here except for the bits array. This is an array which denotes if a particular chunk on a page is free or not. So if a chunk is in use, a bit will be set to 1 for that particular chunk, and if it's not, it will be set to 0. Okay, so since PG infos for medium chunks and PG free structs are stored together with normal chunks, they could be overflowed when an overflow occurs, and could be used to do code injection attacks. We'll demonstrate this using a PG info chunk. So what happens is, for PG info, is we make the page field in the chunk point to the target memory. So this is the normal layout. So when an overflow occurs, we make the page point to the return address. And and we modify the bits array to make all the chunks seem free. So when eventually that page is accessed for a chunk of that page, it'll return our target memory as a valid chunk. As a result, the attacker will be able to write into that information as if it was just memory he allocated. So in this case, we'd overwrite the return address with whatever we wanted to. We can also have an off by one using PG infos. So in this case, we'd overwrite the next field of the PG info. And instead of pointing to the actual PG info, we'd point to a fake one. And in the fake one, we'd have the page again point to our target memory location. And eventually, when the first PG info's page is when the first PG infos page is full, the fake PG info would be used to return the return address as a target memory location. So for PHK malloc, it's vulnerable to heap overflows and off by ones. However, it's not vulnerable to double frees because a check is done before freeing if the chunk is free or not. Okay, we'll describe one more allocator, which is BIM's garbage collector. This is a garbage collector for C and C++. It's conservative, so that means if it thinks value in memory, if it thinks a memory address is in use, it'll not free it, even though it might not be in use. So if it looks like a pointer, it won't free it. This garbage collector will automatically release memory during its garbage collection phase to the system that is no longer needed. As a result, no dangling pointer references should be possible because the allocator manages the memory for the programmer. However, if the programmer does explicitly free memory, dangling pointer reference could occur. So there's a difference between large and small chunks in this allocator. So large chunks are larger than half a page and are rounded up to page size. Small chunks are allocated in pages, and again, as with PHK malloc, these pages are divided into chunks of the same size. So an allocated chunk, unlike the other allocators, only contains data. However, a free chunk contains a pointer to the next free chunk. So again, the same attack could occur. So if an attacker can overflow an in-use chunk and the next chunk is a free chunk, he could overwrite the next pointer and make the next pointer point to a target memory location. Eventually, when the allocator reallocates the free chunk, it will return the pointer's target as a valid chunk. Usually, this is an off-by-4 attack. However, it could happen that this is an off-by-1 attack when there's no padding. A double free can also occur on BIM's garbage collector if the programmer explicitly frees memory. So if chunk 2 is free twice, so chunk 1 is pointing to chunk 2 in this case. If chunk 2 is free twice, it'll be placed at the beginning of the list again. And while chunk 1 still has a pointer to chunk 2. So when chunk 2 is reallocated, it will be writable. so the attacker can change the next pointer, but chunk 1 will still point to chunk 2, so eventually the allocator will return it as a valid chunk, will return next as a valid chunk, and again, the attacker could overwrite an arbitrary memory location. So our conclusion for Böhm's garbage collector is that it's vulnerable to heap overflows, off by 1s to maximum, and generally this heap overflow is just an off by 1 to a maximum off by 4. And a double free is also possible if the programmer explicitly frees memory, which it shouldn't do, but then again, it shouldn't have any overflows either. So our design for a more safe allocator is that on most modern systems, code and data are loaded into separate memory locations. And if we apply the same to chunk information and chunks, we could store the chunk information in separate contiguous memory and protect this memory by using guard pages. However, to associate a chunk with a particular chunk information, we'd use a hash table. So the hash table contains pointers to a linked list of chunk information, and these are accessed through the hash function. So we implemented this in a prototype called distrinet memory allocator, which I'll be releasing later tonight. And we based this implementation on Douglas memory allocator. So this is kind of what the memory layout would look like. So we've still got the text segment. And in the data segment, we have the data section and the BSS section. And for the normal heap section, we have the chunks. And in the maps, in the area where maps are stored, we have a map to hash table and we have mapped chunk information. When the program starts, well, when the program first calls malloc, we map a hash table which is large enough to contain all possible values stored in the hash table. This is pretty large. It's usually 96 megabytes. However, this is just virtual address space because when an area is mapped, it will be used as virtual address space, but when a page is actually used, it will only be allocated by the operating system. So we divide each page into 256 possible chunks, and our minimum chunk size is 16 bytes. So we then separate these chunks into 32 groups of 8 chunks. So for every group in the hash table, we have 1 entry. So this means we have maximum 32 entries in the hash table for every page. And we access 1 element of the group through a linked list of maximum 8 elements. So this is what the hash table would look like on the left. So it contains only pointers to chunk information, and beside that we have the actual chunk information. Hash next is used to store the linked list of maximum 8 elements. And again, we have the forward and backward pointer as the original allocator does to have the doubly linked list of free chunks. We store the size of the chunk and we store our pointers to the actual chunk. So the hash function is designed this way. So to find a chunk information from a chunk, we subtract the start of the heap from the chunk's address and shift the result 7 bits to the right. And then we go over the linked list until we have the correct chunk. We can do this by just comparing the chunk information chunk to the chunk we were looking up. So we also actually need to manage the chunk information area. So we do this by mapping a fixed area of 16,000 chunk elements. And whenever a chunk is removed, so for example, if 2 chunks are coalesced, 1 chunk information will no longer be used, so they will be stored in a linked list of free chunk information. And when we need a new chunk information, we'll just get it from this list of free chunks. If none of the chunks, if we don't have any free chunks, chunk information, we'll just allocate one from the fixed map. If the fixed map is empty, we'll map extra memory, and this region is always protected by guard pages. So we've done some tests to see what overhead we'd have using this memory allocator. So we ran the spec CPU 2000 benchmark 13 times on 8 identical PCs for a total of 108 runs. So what's in red is our maximum overhead, that's 3.69%, and our minimum overhead is minus 0.42%. However, there's also some memory overhead associated with our memory allocator. So the original DL-malloc implementation has about 8 bytes of overhead per chunk. Our current overhead for every program is, well, 1 page for the guard page for the hash table. For every 16,000 chunks, we'll have a guard page for the chunk info region and an information page. Well, currently this information page is not used. I'll talk about that later when I'll tell you what's still to be done in our allocator. And per chunk, we have 20 bytes of chunk information overhead and 1 hash table entry per 8 chunks. Excuse me. So when we ran these, when we tested this memory overhead on the spec CPU 2000 benchmarks, they're generally pretty low, except in the case of 12. However, we should look at what the program's actual memory uses, which is 3 megabytes. So we've enlarged this to 5 megabytes. And 12 uses a lot of really small chunks. At one time, it will use more than 49,000 chunks because we'll allocate 4 chunk info regions. But which brings us to the to-do for dnmalloc. We never release a chunk info region. So if there's lots of free chunk information, we'll just have a very large linked list of free chunk information. So this is what's left to do, which I hope to do in the next few days. If we release this, we'd probably reduce the memory allocation overhead for 12 as well as the other programs I showed. There's also one function in our allocator which is pretty slow. So I'm also going to improve this in the next few days, hopefully, and this should also improve performance even more. So let's discuss related work. So Robertson and a bunch of other people designed a heap protector. This protector stores a checksum in every chunk's header and encrypts this checksum with a global read-only random value. It adds this checksum to the header when a chunk is allocated, and it checks it before it runs free. As a result, if the attacker has modified this, he won't be able to calculate his own checksum without knowing the random number, which is also the weakness of this allocator. If the random value is leaked, it could be bypassed. The almalloc 2.8 implements a slightly modified version of Robertson's heap protector. Contra Police protects the chunk, protects the heap by placing a random value before and after the chunk. And unlike Robertson's heap protector, which modifies malloc and free, this modifies the copy functions, so like string copy, memory copy, and whatever. And it checks if the canary before matches the canary after before executing the copy function. However, if an overflow occurs that in a non-copy function, so for example in a loop, then this allocator is not effective. Again, if the canary value is leaked, the attacker could just place his own canary value on the heap, and as a result, could bypass the protection. glibc added some integrity checks in the latest version. Before unlinking a chunk, it would check if the pointers actually point to sane information. And it will also do some extra chunks in different places of the allocator. For example, before a free, it will check if the pointer which is being freed is smaller than its negative size. This, because this is usually an attack vector. However, Phantasmagoria recently released a paper in which he describes 5 techniques for bypassing these integrity checks, so they're not 100%. So in conclusion, our many memory allocators ignore security issues, and as we've shown, a safer allocator is not necessarily that much slower. But we still have an important limitation in our memory allocator, is that we only protect the chunk information, not what is actually stored in the chunk. So if a function pointer would be stored on the heap, it would still be overflowable. This work is actually part of larger research which I'm doing, which is part of where we separate other important areas in memory from the normal data. So currently we're finishing up on a stack-based countermeasure in which we do the same as we did now. And this is part of my real research, which is building a more methodical approach to designing countermeasures. There's actually 3 papers associated with this talk. The first one describes all these allocators. The second one is actually the paper I submitted to CCC, which describes how we built this allocator using the more methodical approach. And the final one describes the idea for the more methodical approach. So we've got an implementation which will be available tonight on the following website together with the papers. Okay, are there any questions? Yes.
So you're designing a memory allocator which has one very large global data structure, whereas the trend in malloc implementations now is to have thread local allocation buffers. Does does your design sort of scale to the applications that require thread local allocation buffers?
I haven't tested that yet, so I'm not sure.
Because it seems that the performance measurements you made don't really seem to be relevant to modern applications which have lots of threads, and there's a lot of contention over malloc's global data structures, or the traditional malloc global data structures.
That's true. I didn't check for actual threaded applications.
Is there any plans on doing that?
Yeah, hopefully in future versions. Any other questions? Okay, thank you.